Yeah, so this is a Zoom meeting, which we're obviously doing today to make up for the fact that I definitely did not forget that class started at 11. So this is pretty cool. It's kind of like just a video chat, but I can also share my screen with you, so I can go through like presentations and stuff like that, and we can just do it online together in real time.
Oh crap! Oh shit!
Did Charlotte just fall over? Also, Charlotte, this is recording, so everybody will listen to you swear later.
Don't drop any bombs. I'll go back to Evan now. Too much data.
Okay. So this is cool. So this is the first time that I've run Zoom, like a Zoom meeting.
Me too.
So we might see if we can do it a bit more often.
Me too.
Oh
yes.
Now that we know how it works and we can get things happening, which is kind of cool. So I mentioned a little minute earlier about how it's supposed to be raining all Thursday afternoon. Exactly. There's supposed to be lots of thunderstorms or something.
I'm trying to listen.
Pardon?
My phone magnets to the check it out. There's my phone. Look at that.
She can only see my computer.
You see that?
No.
See my phone?
Oh yeah.
Yeah.
Oh wow.
Oh, we're back.
Okay, cool. No worries. Yeah, so I forget what I was saying. Yeah, so it's supposed to be thunderstorms all Thursday afternoon. So we might set it up that we'll do another practical in the classroom this week and then a field trip next week when hopefully it's not storming. So that'll be the plan for Thursday. So what I'll do I'll swap around some of the lectures so that we can do the practical in order. Hang on a second. So I think it's the Hawaiian chain one from memory. Seafloor spreading. Okay, so we'll do the seafloor spreading prac this week instead of the field trip, which means that I might give a brief introduction to the Pacific Ring of Fire, and then we'll do the San Andreas and Hawaii lecture on Thursday before the lab. So let's see how this works. Hold on a second. Let me find the right thing that I want to look at. Actually, yeah, let's just start with this one. Okay, cool. Can you guys see that now?
Yep.
The PowerPoint? Awesome.
Oh, it was there, now it's gone.
Oh, great.
I can in and out. You need to sort out your
My desktop.
Oh, is that yours?
Yeah.
Oh, wait. Oh, there we go.
Oh. Okay.
I thought that was hers.
That's mine.
Had you just minimized me and you were like, the screen's gone, I don't know what's happened, and you've just minimized the meeting.
That's what happened, yep.
Shut up.
The computer did it itself. I didn't touch it.
Okay.
I'm not very tech savvy. Leave me alone.
No, that's fine. Okay. So I'll give a bit of a brief introduction to like some of the plate movements. We talked a bit last week about plate tectonics and introduced the theory of plate tectonics and how plates move. So
Charlotte, get off your phone.
I'm talking to Izzy to tell her to get on this.
Wow. Okay.
Jordan, do you read me? Jordan
was here earlier. He is here.
Classic Jordan.
He is here. He just doesn't want to talk to you guys.
Defend yourself, Jordan.
He doesn't need to if he doesn't want to. All right.
Oh.
Can't you hear
Jordan
me?
said, "Can you hear me?" No, Jordan, we can't hear you.
No, I can't hear you either. I could hear you before when we were talking.
Can you hear me?
Yeah,
Yeah,
we can.
now we can. Now we can.
You can hear me now?
Yep.
Yes, Jordan.
Shut
I
up,
repeat,
Zach.
yes. Jordan, we can hear you.
Sounds like a,
Jordan, hello.
Hello?
Come
Yes.
in, Jordan.
I can hear you, Zach. Hello,
Shut up,
Zach.
like a radio producer or something like that. It'll be like,
Jordan, can you tell us a bedtime story?
What?
Maybe not.
wait, we could. Let's just get back to
Not right now. How about that?
Oh, plate tectonics.
Yeah, so we're talking about plate tectonics and how the plates move. So when we have things like spreading ridges, we have the plates moving apart. And then we have, so they're divergent plate boundaries. When they move towards each other, and we have subduction or continental-continental collision occur, they're called convergent plate boundaries. So the plates are moving towards each other. And then there's also transform boundaries, where the two plates are essentially just sliding past one another. In some instances, they're moving in the same direction, but one plate might be moving faster than the other. It's still called a transform fault, so they're still transform boundaries. So there's three main types of plate movement, and that's those guys there, and they can exist in all sorts of fashions, like adjacent to each other, or in some cases completely different areas. Okay, so transform plate boundaries. So I'm sure everyone's heard of the San Andreas fault. Yeah, yeah. Probably because it causes a lot of problems to Americans, and Americans tend to rule the world.
Yeah.
But so essentially, what's happening is that the plate is moving at the San Andreas fault. It's moving side by side. And if you have a look at this diagram, I'm pointing at the screen, which you can't see. You can just see me pointing mysteriously. If you look at the diagram in the middle, you'll see that.
That one. Or that one.
Yeah, that one.
Your left, my right. What?
On your left. You'll see that there's
I said your left, my right.
there's some spreading occurring. Okay, so there's a number of faults that have spreading occurring, which are the red lines on the image on your right hand side. Okay, so they're spreading ridges, but perpendicular to all of those are transform faults. Okay, so the plate is moving horizontally past each other in that instance. So you can actually see some really cool features. So if you look at that photo, you can see that distinct line between where it's snowy and where it's not. And that is looking at a transform fault. So, or like where the
Very cool.
fault is moving. Yeah.
So then it makes different weather conditions because of the fault.
Yeah. So in this
That's
case,
fantastic.
yeah, in this case,
Never seen it before.
yeah, there's a movement that's occurred that's actually lowered one side of it a little bit.
Elevation
And
means
so
fine.
the elevation isn't high enough for it to collect snow anymore, which is really, really cool.
That's such a good example.
Yeah, I know, right? It's so cool. And
Oh, we have another one.
I feel like you're judging me because I think science is cool.
Science is cool.
What's her name?
Isabel, Izzy.
Welcome, Isabel.
Hey, Zach.
Welcome to class. Today we're learning about plate tectonics.
Thank you.
As you can see, strike and slip faults. These are the topic of the day. The reason why, it's actually snowing on one fault and not the other. The elevation is different, and therefore it can't snow at a lower elevation, but it will snow at the higher elevation. For an exam question, you would draw a diagram and shade it in, and therefore you'd get a 5 out of 4 marks.
As long as you label everything correctly, you're bang on.
As long as you label it correctly, you get 5 out of 4 marks.
Cool. Thank you.
Is that right, Jordan?
That's
Come on,
right, Zach.
Jordan,
Okay.
Houston, we have a problem.
Again?
All right. So when you have these strike slip faults, They, like we said, they offset everything. So particularly, it makes things really fun, particularly when you're looking at river patterns and drainage features. So you'll see in the picture image on your right-hand side how all of the rivers have been shifted along the fault line. So instead of just going across in one clean line, it goes across and then it hits the fault line and then it catches up with where it used to flow straight that has been since been offset. Does that make sense?
Yeah.
Sort of?
Yeah.
Yeah, cool. All right.
Could there be a potential waterfall if like it dropped down?
Yeah, if there's vertical movement, definitely. Definitely.
Gnarly.
Also, which one of you jerks gave me the flu?
I don't know.
I don't know.
Because I have been so sick all weekend and I can only blame one of you kids.
I haven't been sick for weeks.
Same.
Blame on Daria.
Who?
Daria.
Jaria. It was Jaria.
She was a bit sniffly.
She was a bit sniffly.
Is that just because she's not here to defend herself?
No, I could be saying it was Josh, but I don't think it was Josh.
Or it could be Jordan.
Ah, Jordan.
It was probably Jordan.
Honestly,
Probably
it was.
Jordan.
Yeah.
Isn't he just the source of all controversy?
Okay, so this is another example where you can see that, can you see where my mouse is on your screen?
Yeah.
Okay, so you
That's
can
so
see,
weird.
Like the biological mouse or the computer mouse?
in this case, it's the computer mouse. You can also
I can see
see
that.
I don't know why I always have those things with me. Okay, anyway, so you can see these lighter layers, lighter sedimentary layers here have been offset and they're over here in this side. So you can see how the two plates have shifted side by side. Can everyone see that? Charlotte can't because she's not paying attention.
What?
So San Andreas is a massive sequence of transform faults. So strike slip faults. So there's the two continental plates are shifting side by side. In the main part of the San Andreas, what have I just done?
Jesse.
In the main part of the fault, down here, it's continental, and then up here it's oceanic continental. When you start getting into the northern part of the North American plate. What is that face, Charlotte?
I think she's frozen.
Oh. Oh, Charlotte, you have such a good freeze frame on right now. I can't wait for you to rewatch this video. All right. So you can see here the collection of those transform faults where the material's moving. If you have a look over here, this is the South Island of New Zealand. New Zealand's actually really fascinating because instead of just being two tectonic plates that are shifting past each other like this, on one side of the transform fault, you have the Australian plate subducting underneath the Pacific plate, and then on the southern end of the transform fault, you have it doing the opposite. So you have like that transform fault is essentially twisting because there's two subduction zones going in the opposite direction, which is really cool and also explains why New Zealand is so tectonically active, essentially. Does that make sense, what I just said?
How many? Hold on. So there's one main, right? And then there's like offshoots.
So these black lines here are the fault zones. And at either end of those fault zones, at the either end of the transform fault, there's subduction occurring.
Right.
But at one end, the Australian plate is subducting underneath the Pacific plate, and at the other end, the Australian plate is going over the top of the Pacific plate.
Right.
So instead of being all subducting in the same orientation, that's why there's so much faulting in New Zealand, is because it's both plates are trying to subduct underneath each other, which is really weird and only really occurs there. All right. So
bit loud, eh?
All right. So you can see another example here of how these rivers get offset by the movement of transform faults. Okay.
Mhm.
And obviously, when you have transform faults, you have a lot of earthquakes associated with that. So what happens is that the friction builds up, and so there's more and more stress build up as the plates are trying to shift past each other, and then eventually they will shift, and that sudden movement will release a mass of energy, and that's what causes these big earthquakes that tend to cause a lot of problems for the millions and millions of people that live on top of the San Andreas Fault.
Like the movie.
Pardon?
Like the movie San Andreas.
Yes, except probably less. I was just about to say less sexy because Dwayne Johnson's in it, but whatever. Yeah, so you can see here that there's a number of faults in San Andreas, just like.
Or does it only work in the
I tried, but it didn't work. Would have been cool, so we didn't have to see butting heads.
What? Okay. I don't know what you two are up to, but that's fine. So I'm just going to skip ahead a little bit. What we're going to do on Thursday is we're going to try and calculate how fast plates move. So I mentioned this a little bit last week, where we can look at the different types of volcanic rocks that have been made and give ages to them. And so, for example, if we look at either the Emperor Seamount chain or the Hawaiian Island chain, we can physically measure distance and then divide it by age to be able to give us like kilometers per year movement kind of thing, which is pretty cool. So that's the kind of calculations that you're going to be doing in class on Thursday. Sorry about that. That was probably altogether unpleasant. So the types of volcanoes you guys are probably used to is the peaking kind. So the really like this type of volcano over here. Okay. So that's a different type to the type that we see in Hawaii. They have like this one, which is the Mauna Loa. Okay. And they're called shield volcanoes. And so the reason that they're so big and so flat is because the lava that flows out of them is really liquid, okay? So it has a lot less silica in it. So remember how I was talking last week when we had that big breakdown on the board about the different kinds of igneous rock types? And I was saying that mafic rocks don't have very much, like they don't have very much quartz in them, and the silica that's in those rocks is what makes them essentially sticky. So these types of volcanoes that you see up here have a really sticky magma, okay? So they don't flow very fast and they don't flow very far. But the shield volcanoes that we have in Hawaii flow really well, and they flow really wide, and that's why you have these low-lying flat islands and volcanoes occurring. So yeah, so here is an example. So you can see how this viscosity works. So if you have a low viscosity, so something like your basaltic magmas have a low viscosity, and they just flow and spread out and continue flowing until there's no more source for them to flow. When you have something that's got a high viscosity, or in this case, magma that's rich in silica, so something like a felsic magma, they don't flow as well, and they are sticky, and they build up. All I can think of when I look at this image is like, why would you just straight up pour honey on a bench? Like, that's just asking for ants. The reason that it works like that is because of these guys. So these are silica tetrahedron, okay? Essentially all you need to know is they're just like little pyramids that stick together at each end of the pyramid. And the more of those pyramids you have, the more sticky the lava is, or the magma is. So something like a basalt does not have very much silica tetrahedron in it at all, so it's not very sticky. Okay. Sorry, I just got your meeting will finish in 10 minutes. It's like, fine, we'll finish in 10 minutes. That's totally fine. So what happens is the way that Hawaii has formed is that there's that hotspot underneath it. So there's that rising mantle plume that is stationary, and the plate is moving over the top of it at a set speed. And that speed is set by things like subduction, or the spreading at the other end of the plate, and that's all driving how fast this whole plate is moving. Okay. So we're going to be having a look at some of the fun stuff. So yeah, so the active volcanoes here in Hawaii, they're our youngest, obviously, because they're still erupting now. And then the further we get away from Hawaii, the older those islands get. And so what we can do is say between this age and 0, it has moved however many kilometers it is between those two islands. Does that make sense? Yeah? Cool. All right. Yeah, so the way that it works is if there's a mantle plume underneath, and the heat from the mantle plume causes the area to rise a little bit, and as the hot material is coming out of the volcanoes and things like that, it's rising, and then as the plate moves further along, and it starts to cool down, those mountains start to sink. Okay. And so the volcanic mountains start to sink down into the ocean, and are no longer as tall or as large as they were originally. Did someone just ask a question?
No.
No, that was somebody's background. So what we can do is we can track where the hotspot is by where the active volcanoes are. The Hawaiian chain isn't the only hotspot in the world. There's one, I think I mentioned last week, that there's one between Tasmania and the mainland that's forming a little island chain between us at the moment. So a lot of the basalts that are found along the east coast of New South Wales, so like mostly parts of the Great Dividing Range, were formed from the hotspot travelling, well, our plate travelling up over the top of the hotspot. So there are igneous rocks in Australia that are relatively young, and it's from the Australasian plate travelling over the top of this hotspot, which I think is pretty cool. I don't know about you guys.
So cool.
I was like, we've already discerned that I'm a huge nerd. Okay, so just a thinking question. If we had a tectonic plate that was moving steadily to the northeast, so the plate's moving steadily to the northeast over the top of a hotspot, what direction would the chain be aligned?
Northeast.
Yeah, so you would see the hotspot chain being developed in the same orientation that the plate is moving.
Yeah.
So at which end of the chain would the oldest volcano or seamount be?
At the lowest point where it started.
So if it's moving northeast,
It would be down here.
so if this is where the hotspot is, and our plate's moving over the top of it,
It'll be up here
it'd be up here.
The oldest one.
Yeah, will be
because it's moving up.
hotspot.
Oh.
Yeah, so the youngest one will still be forming now, and the oldest one will be up here somewhere. Yeah. Just some things.
Cool.
I have put in this because I love talking about Hawaii and the Icelandic volcanoes, which I'm not even going to try and pronounce. But I've put a lot of videos into this PowerPoint, which I have uploaded up onto Moodle, so you'll be able to have a look at it later. But just to show you how quickly these lavas flow. Okay, so definitely check out some of these videos.
Yeah.
Because it's actually really cool because they flow so fluidly. There are a few. Hang on a second. Yeah, so you do get a few different types of basaltic lava. Okay, and both of those depend on how much silica is in the particular basaltic lava. So this crumply stuff up here is called RR lava, and the ropey stuff down the bottom here is called Pahoehoe lava. So Pahoehoe. So the way that I always remember it, if my first year lecturer told me, and I've never forgotten it since, the way that you remember which is which is that if you imagine what it would be like to walk barefoot over the top of them, if you were walking over the top of this, you'd be like, oh, lava. I have never forgotten it, and it still sticks with me today. So just a quick way to try and remember how they work. Another really cool feature of basaltic lava is these things that are called lava tubes or lava tunnels. So the lava flows through so quickly that the outside of the lava starts to crystallize, obviously because it's cooler on the outside, but everything inside it is still hot and molten and flowing, and it just flows out and creates essentially like a lava pipe. Are you guys messaging each other?
No, it's just a group chat that I have for ICT and learning.
People are messaging me to go to dinner. I mean, to go to lunch.
Oh. I was like, whoa, someone's got a hot date. So they crystallize on the outside and they form these really cool tunnels, and you can actually walk through old lava tubes, like where lava of over 1200 degrees Celsius was just flowing through like liquid water, which is really, really cool. So this photo here was taken last year or the year before perhaps, where the lava was just pouring out so fast that it was like a fire hose coming out of the crack in the earth. So this is liquid rock that we're seeing pour out into the ocean here, which is just really freaking cool. Yeah, and so there's a bit of news there. I don't know if you guys were aware of what was happening in Hawaii early last year.
Yeah.
With the big lava flows, and the huge amounts of sulfur dioxide gas that was pouring out. But yeah, so this is how quickly the lava can flow. It's just starting to flow into other people's backyards and things like that. And here we've just got where, because it was such a big eruption, there was a bit of shaking, and so there were cracks that were forming, and sulfur dioxide gas was just pouring out of these cracks in the road and in the middle of the forest and all sorts of things. So if you're asthmatic like me, potentially life-threatening, and all around bad smelling. Has anyone ever smelt sulfur dioxide gas before?
Is that sort of like the smell in like Rotorua in New Zealand? Yeah.
Rotten eggs. It's nasty.
Yeah.
It's nasty. So that stuff was pouring out everywhere. So one thing to think about, if we have like an effusive volcano that's got magma pouring out so quickly, would you expect there to be a tsunami associated with it? No, probably not, because it's not associated with earthquakes. Yeah. So yeah, I think that the recording is about, like the meeting is about to stop. And so we can go over the rest of this later, but thanks for joining, guys, and I'm sorry that I keep coughing and I'm really snotty. It's gross. It is one of your faults, and I blame you all collectively. Yeah, So thanks for joining. And I am sorry that I missed today's lecture.
That's all good.
And hopefully, if I can get this set up